Good morning, all of you. Today we will start with the differentiation. First, we revisit the function of bounded variation, positive variation and negative variation, total variation, and Jordan decomposition theorem. We will revisit quickly. Then we will discuss about the differentiation of an integral with respect to some of the theorems. You know that a function f is said to be bounded variation. If t is finite, then we say that f is a bounded variation. So we take an interval of a comma b is an m. In that interval, it is a bounded variation. Means if you make a t of a comma b is finite, then we say that it is a bounded variation. And also we discussed in the last class, if f is a bounded variation on closed interval a comma b, then the t of a comma b is equal to p of positive variation plus negative variation, and f of b minus f of a means that is an integral representation of a to b f of x dx. Then that can same as p of a comma b minus n of a comma b. That is the f is bounded variation. These two conditions are holds good. This we proved in the last class. And also we proved the Jordan decomposition theorem. What is Jordan decomposition theorem tells? A function f on a closed interval a comma b is a bounded variation if and only if it can be expressed as the difference of two real valued monotonic function. You know that already the bounded variation function can be represented as positive variation as well as negative variation. Then that is f of x minus f of x can be represented as g of x minus h of x. These two are the representation. Then this theorem we already proved. T of a comma b is less than infinity. Then g and h are monotonic function. Then we say that can be expressed as a difference of two monotonic function. Suppose any problem is given, then we can express the given problem can be make it into a difference of two function, and also you can check that it is a monotonic condition holds, means monotonic increasing or decreasing. Then we say that it is bounded variation. This is the one way of proving the bounded variation. We will discuss in the later classes how to solve the problems of bounded variation. Now, today's lecture, we will mainly concentrating on the differentiation of an integral. In this, some of the important theorem related to differentiation of an integral. Before that, we can recall some of the basic definitions are needed to prove the theorems. Here, the derivative of an indefinite integral of an integral function is equal to the integrand almost everywhere. This we recall. And also with this theorem we already proved, means it is a continuity property of an integral. Using that also, it is needed for the proving one more important theorem related to integrable function. Like f be a non-negative function, which is integrable over e. If this condition holds, then given epsilon positive, there is a delta positive such that for every set, if you choose any set in that integrable over a set function, that a is contained in E with the measure of A, the measure of that subset is less than the given, establishing delta less than delta, we have that integral upon f over A is less than epsilon. Means this is the continuity of the non-negative function which is integrable over E. Now we will prove the theorem. If f is an integrable on closed interval a comma b, then the function capital F is defined is f of x is equal to integral upon e to x f of t into dt. This is small f is integrable function over the then capital F of x is continuous function of bounded variation. If this is integrable, then definitely this is continuous function of a bounded variation on closed interval a comma b. You know that if it is an integrable function, then definitely using this star, we can say that it is continuous. This is not cancelled. From star, it follows that capital F is continuous. Now we only to prove that this capital F is a bounded variation. You must remember, whenever we are proving a bounded variation, first we can make, using that interval, we can make a subdivision. Subdivision of that interval and make a summation of the difference of the function with the previous one, the modulus. That is the first procedure of a bounded variation. Using that property here, let us start the proof. Let f is a bounded variation. Consider a subdivision. AB is the closed interval that can be make it into a subdivision here. A is equal to x naught less than x1 less than etc. xk, and we form a ki running from 1 to k mod of f of xi minus f of xi minus 1. Here, what is capital F of x? Here, capital F of xi means it is the interval ranging from a to xi, small f of t dt. This is capital F of xi minus 1 is the, again, we can represent that as integral upon a to xi minus 1 f of t into dt. You know that if you expand this interval a to xi minus 1, this xi up to xi a become cancelled with each other because the lower limit and then minus sign become cancelled, or we can use the properties of integral upon a to b and minus integral upon a to c means, you know that the lower become cancelled, you get the xi minus 1 to xi f of t into dt. The simplification of this. Then definitely if the modulus function will be there means we can interchange the sum with respect to integral, it is less than or equal to summation I running from 1 to k integral upon xi minus 1 to xi mod f of t dt. Because we already know that f of f is a integrable function, it is finite, integral upon a to b mod f of t dt means it is both having a positiveness, then definitely it is finite. Finite means it is integrable. Then if you take a supremum, because here if you take a supremum over all the subdivision, then we can make this as t of, if you take a supremum of this of all the subdivision, we get t of a comma b over f is less than, because already shown that it is finite. This implies that f belongs to bounded variation. Now we will recall some of the little bit first principle. Let E be a given set of the following condition, because this is useful for some of the open set or closed set properties for proving the next theorem. Let E is measurable. Given epsilon positive, there is an open set O is contained in E. Then with measure of E, O is contained, O means open set is contained in E with superset of E with M star of O x E less than finite. Similarly, given epsilon positive, there is a closed set F is contained in E with outer measure E minus F is less than epsilon. There is a G in G delta with E is contained in G with outer measure of G minus E is equal to 0. Exactly similar way, there is an F in F sigma sets are Borel sets, with F is contained in E with M star of E minus F is equal to 0. Using this little bit principles of a set function, now we will prove the one more theorem. If F is an integrable on closed interval a comma b and integral upon a to x f of t dt is equal to 0 for all x is in the closed interval a comma b, then small f of t is equal to 0 almost everywhere on closed interval a comma b. You know that if f is integrable on closed interval a comma b means integral upon a to b f into dt is equal to less than infinity. But here there is some point x lies in this interval, then integral upon a to x f of t dt is equal to 0. If this is the condition holds means definitely this functional value of t must be 0 almost everywhere on the closed interval. Now we will start with how to prove this one. Suppose let f of x is greater than 0 on a set E of positive measure m star E is less than 0. You know that if is any set we are chosen, because there is an open interval means definitely there is some sets will be there that may be open or closed. But here it is given it is a closed set, then definitely E is of a positive measure, outer measure of E is positive, then by little word first principle there is a closed set F must be contained in E with measure of F is positive. Then definitely we can write let G is equal to open interval with respect to minus F, then G is an open set. Now either integral upon a to b f of f is equal to 0 or any, if this is an open set, definitely any one of the condition may be holds. Suppose a to b f is not equal to 0 is a contradiction to the hypothesis, because this is only possibility is this one. Therefore, suppose integral upon a to b f of f is equal to 0 means then integral upon f over g can be splitted as integral upon f over a to b minus integral upon f over, we are chosen capital F is a closed set. We using that one, the outer measure, this implies this is 0 is equal to integral upon a to f, a to b is equal to integral upon f over this one. We will rearranging this goes to right hand side, then integral upon a to b f is equal to integral upon f over g plus integral upon f over capital F. If f is greater than 0, definitely the measure of f is positive. Means measure of f is positive, then definitely it is not equal to 0. If any one of them is not equal to 0 means definitely integral upon f over g is not equal to 0 minus integral upon f over f. Any open set on a real line is a open set can be written as countable union of disjoint open intervals. Here we can make this as a real line because in the open interval a comma b means then definitely it can be written in the countable union of disjoint open intervals. Definitely G can be written as union of n running from 1 to infinity an comma bn. Each a1, a2, a1, b1, a2, b2, a3, b3, etc. You get a many disjoint open intervals. In that is, and also you know that ai is not equal to aj because disjoint means ai intersection aj must be equal to mt. Integral upon f over g is equal to summation n running from 1 to infinity, because union becomes summation in the measurability of the sets, then definitely it is an to bn f is not equal to 0. This means that integral upon an bn f is not equal to 0, at least any one of the values. You know that this can be split as an bn 1, 2, etc. Either any one of them, a to an, if not equal to 0, or integral upon a to bn. We can split this a to bn can be a to an to bn. This is the simple form. You already know this. Using this property, here both the contradicts the hypothesis. Means definitely a similar contradiction can be done if f of x is greater than 0 on a set of positive measure. This is the proof for if f is integrable on closed interval ab and integral upon a to x f of t dt is equal to 0 for any value of x belongs to c a comma b, then f of t must be 0 almost everywhere on it interval a comma b. Now we will prove important theorem, one more important theorem. If f is bounded and measurable on a closed interval a comma b, and capital F of x can be represented as integral upon a to x f of t dt plus functional value of a f of a. Then if this is the condition, if is bounded and measurable in the interval a comma b, then capital F of x can be written in this form. Then f dash x is equal to small f of x, means the derivative of the function is equal to this one for almost all x in closed interval a comma b. Here what is given? Given function is bounded and measurable. Almost all x in closed interval a comma b. Means you know that bounded definition. Since f is bounded, like mod f must be less than or equal to some positive number, that is we represent here k. And also you know that fnx can be written as, because it is a differentiable function, capital F of x, x plus h minus f of x divided by h. Means h can also be written as 1 by n. Sometimes a is lying between capital x, x is lying between the interval a to b. Then here we can write fnx is equal to here n times integral upon, because 1 by h we are represented as n, a to x plus h, f of, you know that h is the step interval general, f of t dt minus integral upon a to x f of t dt. Then n is equal to the combination of this, or combined version of this can be written as here x to x plus h, because these two become subtracted, you get x to x plus h f of t dt. Then you know that modulus, it is bounded, mod of fnx is less than or equal to n times integral upon x to x plus h f of t dt. The modulus can be taken inside, then that become less than or equal to n times integral upon x to x plus h mod f of t dt. Here mod f of t means we are taken as k, because f is a bounded function. F is a bounded means it is less than or equal to k. Then n into k integral upon x to x plus h dt. 1 into dt means you get t. T can be applied, that is upper limit is x plus h minus x. Xx become cancelled, you get h only. H into n means it is reciprocal to each other, then definitely it become cancelled, you get k. Means mod fnx is less than or equal to k for every n, and also for every x is in lying between the interval closed interval a comma b. Means the given sequence is, f is bounded is given. Here we are arrived. Fn is a bounded sequence. Fn is a bounded sequence means definitely it is converges. Fnx is converges to f dash x as n tends to infinity. You know the bounded convergence theorem. If it is a bounded, then we can apply that theorem. We have there is a some point C lies between closed interval a comma b, then integral upon a to c f dash x dx is equal to limit, because we use bounded convergence theorem here, limit of n tending to infinity integral upon a to c fnx dx. Then this fnx can be replaced to our function. You know that we are taken as here fnx is equal to capital F of x plus h minus f of x divided by h. You know that differentiability and integrability are reverse process. Using this property 1 by h f of x plus h minus f of x dx, then we can split this into a plus h into c, because the inner point, the limit can be changed, then that become a plus h to c plus h. Here a to c f of x dx. If you apply here limit of 1 by h, this become f of c and this become f of a. That function become cancelled with each other. Then you get integral upon a to c f of t dt. F of t d integral upon f of t dt is exactly similar, equal, means then we can transfer to that one into right hand side a to c f dash x minus f of x dx is equal to 0. Means the integrand function is equal to 0. Means definitely the f of x is equal to 0 almost everywhere. Means this function is 0 almost everywhere. Hence, f dash x is equal to small f of x, means we can rearranging this. You get capital F dash x is equal to small f of x almost everywhere. This is the one of the important theorem. There are two theorems will be there. One of them is bounded and measurable and this condition. And one more theorem we will prove now, that is like f is an integrable function on closed interval a comma b, and let f of x is equal to integral upon a to x f of t dt plus capital F of a into 1. Then f dash x is equal to f of x for almost all x in closed interval ab. You can observe the previous theorem here, bounded and measurable, and this theorem is also holds in terms of f is integrable function. Don't confuse with both the theorem. Which one they will ask, you must write that one only. Here, without loss of, how to prove this? Without loss of generality, because it is an integrable function. Make a two separate set function. That set function may be in the generalized function. Then you get the proof. Without loss of generality, here we are assuming that f of x is greater than or equal to 0 for all x in closed interval a comma b. That's why we define a function fnx is equal to f of x if f of x is less than or equal to n, and n if f of x is greater than n. Here, if this is function itself positive, means f minus fn is also greater than or equal to 0. Here gnx, we chosen this function as gnx integral upon a to x f minus fn, because here a to x is there. That's why we are choosing here a to x is the limits, then a to x f minus fn. Some of the books they are written here dx also, but this is also a standard form of the function. Suppose you can put brackets into dx, that is same as this one. Then here gn is a increasing function for if x is less than y. Then you can choose GNY is equal to means same, but instead of X, because X is lying in Y, therefore A to X, F minus Fn can be written as plus X to XY, F minus Fn. This is greater than or equal to integral upon A to X, F minus Fn. Means Gn of Y is greater than or equal to Gn of X, means it is an increasing function because F minus Fn is positive, greater than or equal to 0. Means it is a monotonic, therefore Gn dash exists almost everywhere and positive by using the bounded and measurable function d by dx of integral upon a to x fn x is equal to fn x almost everywhere. Then if this is the function f dash x is equal to d by dx of gn plus d by dx of integral upon a to x fn, this is greater than or equal to fn x almost everywhere. Means if you choose letting this n tending to infinity, we get this as this become 1, you get f dash x is equal greater than or equal to fn x become n tends to that convergence property f of x almost everywhere. Here, if you are applying integrating with respect to the closed interval a comma b, then integral upon a to b f dash x dx is greater than or equal to integral upon a to b f of x dx, because you know that this is the indefinite integral, definite integral that become f of b minus f of a by 1, because the given function is integrable function. Using that property, this is fb minus fa. Here we are arriving integral upon a to b f dash x is greater than or equal to, but general opinion, you know that integral upon a to b f dash x dx, that is differentiation theorem, we proved in the first class, that is less than or equal to fb minus f of a. Then if using these two, this become equality. Integral upon a to b capital F dash x dx become fb minus fa. fb minus fa means integral upon a to b f of x dx. Then we can rearrange because the limits are same. Then integral upon a to b f dash x minus f of x dx is equal to 0 by the properties of basic integration, we can get this one. Then definitely by using previous first theorem, whatever we proved, that using that this inner function is f dash x is greater than or equal to f of x almost everywhere, or is equal to f of x almost everywhere, we get f dash x is equals, you must write f dash x minus f of x is equal to 0 almost everywhere, means f dash x is equal, capital F dash x is equal to small f of x almost everywhere. These two are important theorems, you must remember and work it out. Okay, is any doubt? And some more theorems on bounded variation we will discuss in the next class.